Yes, this is the problem I'm going to do. So this is, I actually made it. Look, it's a wire with a bead on there, and it can rotate. Yes, I'm going to solve this with Lagrangian mechanics. Yes, I've done a ton of Lagrangian mechanics problems lately. But the thing is, like in classical mechanics, there are a bunch of cool problems you can do, and I want to do them all. But I have to do this one because it's a very, very common problem to see, and I thought we could just do it. So I'm going to do it on the board, and then I'm going to use SymPy to check my answer, and then I'm going to model it in WebVPython. And even then that won't be done because there's some other stuff that you can do. But let's just get started. Okay, so I have here a circle rotating with some constant angular velocity, and then I have a bead that can move up and down on there. And the first thing we should think about is, well, how many degrees of freedom do you have here, right? And it looks really complicated, right? Because this is going to be moving in 3 dimensions. However, this motion is set. I can't change that. So that's not a degree of freedom. Really, the bead can either go this way or that way. So it can only go up and down the wire. So that's really just 1 degree of freedom. And that may seem crazy. It is a little crazy, but that's the way it is. And where to put my chalk? Okay, I got my chalk. So let's go ahead and write down our 1 variable for the degree of freedom. So I have that omega. I have a wheel of radius r. And then this is going to be equal to, let's call this the angle theta. Now, I do need to consider 3 dimensions. And I want to write the Lagrangian. So the Lagrangian is going to be equal to t minus u. And the kinetic energy term I have to worry about here. I keep rotating the wrong way. Because how do I write that in terms of theta and theta dot? And the answer is I don't know. So instead what I'm going to write is the Cartesian coordinate version of this. Because I know in Cartesian coordinates I have to have 3 variables here, so this really makes it kind of interesting. I have t is 1/2 m x dot squared plus y dot squared plus z dot squared. And then the potential energy, let's call this the z direction. So the potential energy would just be mgz. Okay, now, how do I get a relationship between x, y, and z and theta? That's the question. And then I can take those derivatives. Let's just start with the z direction first. It's a little bit easier. I'm going to write them over here because we're going to use them more than once. Z is just going to be, let's call this the origin. So z is just this distance right here. So if that's r and that's theta, this is going to be negative r cosine theta. Oops, hit the camera, sorry. That's not too bad, right? Okay, now that I have that, that's the projection of this onto the z-axis. This is the projection onto the xy plane. So xy plane. So in this position right here, it would have no y coordinate, but it would have an x coordinate, and that x coordinate would be r sine theta. But how do I take into account the fact that that's rotating in the z direction? Well, now I can just change that angle of rotation. You can imagine looking at it from the top. So up here, so if I have it like that, then as I rotate that, I'm going to go through the different angles and project that into the xy plane. So I can just multiply this by sine omega t. So that's the projection into the xy plane, and that's the rotation from the hoop. And then the y would be the same way. Y would be r sine theta. That's the projection into the xy plane, cosine omega t. That's an omega. So I have it. Okay, now we have to take the derivatives of these respective time and then square them and then add them together. And it seems daunting. And in fact, it is in a certain way. But we're going to do it anyway. So let's make sure that we have plenty of room. And I'm just going to start with x dot. X dot is going to be equal to the derivative of this. Now we have 2 things that depend on time here, right? I have both theta and omega t. Well, t depends on time. So I'm going to take the derivative of this term right here. So that's going to give me r theta dot cosine theta. So I took the derivative of sine theta and I got cosine theta, but then I have to take the derivative of theta and I get a theta dot. And then I have this term sine omega t. And now I need to take the derivative of this, so I'm going to get an omega term in there. So it's going to be plus r omega sine theta cosine omega t. Is that good? Okay. Now let's do the y dot. That one's pretty easy because it's essentially the same thing, right? I'm going to take the derivative of this. I get r theta dot, that's equal. R theta dot cosine theta cosine omega t. And now I'm going to take the derivative of that term cosine, so I can get a negative r omega sine theta sine omega t. And then finally I'm going to do the z. That one's pretty easy. Z is going to be negative r, positive theta dot sine theta, because the derivative of cosine is negative sine. Okay, now I have to square these. Let's hold off on the z direction. I'm just going to square the x, and I'm going to square the y, x dot, y dot. And then I can add those two together. So let's do that. So x dot squared is going to be this term. So r squared theta dot squared cosine squared theta sine squared omega t. Now I'm going to square that one, and then I'll do the cross term. Plus r squared omega squared sine squared cosine squared omega t. Now I'm going to use a shortcut because I know the answer. I'm cheating, but you shouldn't cheat. I'm just running out of room here. So if I get the cross term, I'm going to get this times this, two of them. So I'm going to put 2r squared theta dot omega, then stuff. There's stuff, right? I'm going to have a cosine theta, sine omega, sine theta, cosine. I get every combination. Now let's do the y dot squared. Y dot squared is going to be this r squared theta dot squared cosine squared theta cosine omega squared t. And then I'm going to get that squared plus r squared omega squared sine squared theta sine squared omega t. And now I'm going to get the cross term. I get minus 2r squared, that's a squared, theta dot, no, it's not. It doesn't really matter. Omega. But then I get the same stuff, right? I have cosine theta, cosine omega t, sine theta, sine omega t, so I get all the same stuff. So now look what happens when I add these two together. X dot squared plus y dot squared. Okay, that term and that term cancel. Boom! That's nice. Okay. Did I hit the camera again? I did, didn't I? Don't make me redo this whole video just because I keep hitting the stupid camera. I did do that wrong. I put up my camera wrong. Oh well, my fault. I'm going to hit the camera again. Okay, so now those terms are gone. Right here, I can factor out r squared theta dot squared, r squared theta dot squared, cosine squared, cosine squared. So let's write this as r squared theta dot squared, cosine squared theta, and then I have sine squared omega t plus cosine squared omega t. Well, that's nice. Okay, so that's that term right there. This term, I'm going to factor out the r squared omega squared sine squared, oh, I meant the sine. Sine squared, so I get plus r squared omega squared sine squared theta, and then I have cosine squared omega t plus sine squared omega t. So here we have that term, sine squared plus cosine squared, 1. So it's much nicer. And then look at this. Now I can factor out, oh no, I can't. I can't factor that out. Okay, now let's get the whole kinetic energy term. T is 1/2 m x dot squared plus y dot squared. So I have r squared theta dot squared cosine squared theta plus r squared omega squared sine squared theta. And then I have my z dot term squared, which is going to be r squared theta dot squared sine squared theta. But look at that mess. It's kind of pretty though. So over here though, oh, that's 1/2. That's right. Okay, right here I have r squared theta dot squared cosine squared theta, r squared theta dot squared sine squared theta. I can factor out the r squared theta dot squared, and I get cosine sine squared, so it's 1. So this is just going to be equal to 1/2 m r squared theta dot squared plus r squared omega squared sine squared theta. All that stuff, right? And we get something pretty easy. But you got to do the work. Okay, now let's write the Lagrangian. I can do that in one fell swoop up here. L is t minus u, so it's going to be this 1/2 m r squared theta dot squared. Did I run out of room? Okay, I'm okay. Plus r squared omega squared sine squared theta. And then minus the potential, and the potential is mgz, but that's got a negative sign right there, so it's going to be plus mgr cosine theta. That's not too bad. Okay, now the Lagrange says partial of L with respect to theta minus the derivative with this of partial of L with respect to theta dot is 0. So let's do this one piece at a time. Partial of L with respect to theta. Okay, I'm looking through scanning. Boop, there's a theta. Okay, so if I take the partial of this respect to theta, I have the power rule. So I'm going to get a 2 down front. I'm going to get m r squared omega squared sine theta. But then I have to take the derivative of sine theta. The derivative of sine theta is cosine theta. And then I have to take the derivative of theta, so I get theta dot. And then that term is going to be equal to minus mg r sine theta. I'm sorry, I don't get the theta dot. I don't get the theta dot because I'm not taking the derivative with respect to time. I'm taking the partial derivative with respect to theta. So that's just partial of theta with respect to theta is 1. Now let's do this. So I'm going to start off with the partial of L with respect to theta dot. Scanning, there's the theta dot. So I get m r squared theta dot, right? Because I bring the 2 down for the power rule. Now there's no other theta dot, so I'm done. And I can take the derivative with respect to time. That's the only thing that depends on time, so I just get theta double dot. Now I can put it all together, right? So this minus this is equal to 0, so this is equal to this. So this is equal to this. That's it. So I can write m r squared theta double dot m r squared omega squared sine theta cosine theta minus mg r sine theta. And I want to solve for theta double dot. Divide both sides by mr squared. So I get omega squared sine theta cosine theta minus g over r sine theta. Okay, so one of the things we can do is to check limiting cases. In this case, if I have my rotating thingy and it's not rotating, then this just can move up or down like that, and it actually is the same as a pendulum. I know the equation of motion for a pendulum, so what happens in my solution if omega goes to 0? Let's just see. So if omega is 0, this whole term goes away, right? And I just get negative g over r sine theta. That is the equation of motion for a pendulum. So that's kind of a nice thing. If you want, you could write this as sine of 2 theta over 2, but I'm just going to leave it like that. We can deal with this later. But what I want to do now, because we can model this in Python, and that's what we're going to do. We're going to model this in Python. But I want to double check in SymPy. Since I showed you how to use SymPy, I'm going to show you how to really quickly do this same calculation in SymPy, and hopefully I won't make a mistake. I make mistakes here, but let's just see. 'Cause I'm not the greatest at this. Remember, a lot of Python is like being a wizard, and you're looking at a spell book and you're just saying cast this spell, and so the spell I'm going to cast is solve this algebraically. Okay, so I've already imported SymPy. What I need to do now is declare my variables as symbols. So I can do that. Oops, and I'm in my cell. I'm using Jupyter Notebooks. T, M, G, omega, R. Those are the variables I'm going to use that are just variables. I want those in my solution. And so those are going to be symbols, sp dot symbols, and then I can say what they look like. So it's going to be T, M, G, omega, R, right? So did I miss one? T, M, G, omega, R. Okay, I think I got them all. And that's just one, it's going to make me able to display them as things. And so I can display omega, as the Greek letter omega. Now I do have another variable, and my other variable is going to be theta. Theta is going to be sp.symbols, but it's different. It is, I'm going to represent that. Okay, I got to put this R right there because otherwise if I start with a slash, it's going to return. So R theta. If you want to just use a normal word, that's fine. And then I'm going to give it a class of function. So that means that theta is going to be a function of something else. T, M, G, omega, R are just values. Now I can define theta as a function of time. And just so you can see, if I print theta, I get an error. Symbols takes one positional argument, but two were given. What did I do wrong? See, you knew I was going to make a mistake. Oh, class equals. There, good. Okay. I told you I was going to make a mistake, so that you can't really get surprised. Okay. Now I'm going to define some other variables. I'm going to say theta dot is the derivative of theta with respect to t, so that's sp dot diff theta t. Theta double dot is the derivative of theta dot with respect to t. Good. Okay. Now I need to define my x, y, and z. X is going to be equal to, I already wrote this down, right? R times sine theta sine omega t. So sp dot sine theta times sp dot sine omega times t. Y is R times sp dot sine theta times sp dot cosine omega times t. And then z is negative R times sp dot sine cosine theta. Now I can go ahead and define my kinetic energy. T is sp dot rational, because I want to write a fraction, 1 over 2 times m times the derivative of x squared, so sp dot diff x t squared plus sp dot diff y t squared plus sp dot diff z t squared. Okay, so that's my kinetic energy. Let's just print that. I'm going to simplify it. See if we get similar to what we got before. Okay, that seems the same. That's good. Then I can say U is m times g times z, and L is t minus u. And I can print that if I want to, but I'm not going to. Now I'm trying to just check, right? I've already gone through this in another video. Now I'm going to make the Euler-Lagrange equation. LE is equal to sp dot diff L with respect to theta minus sp dot diff of sp dot diff of L with respect to theta dot t. So that's the derivative of L with respect to theta dot, and then I take the derivative of that with respect to t. And if we want to, we can print that. LE dot simplify. It's going to take a second. Okay, you see that's what I got. That's the same thing that I have right there. You can verify that. I could solve for theta double dot, but I already did that. It wasn't too hard. But this was just like a little check, a safety check, okay? When the algebra gets really hard, it's useful to be able to do this. That one wasn't that bad, so it's okay. Okay, let's go over and model this. This is what you really wanted to do. Model this in WebVPython, because I can do that. Now, I kind of feel bad. I shouldn't have used the z direction, and I was thinking about changing this just to orient things, but I'm not going to. So let's just start putting in some values here. G equals 9.8. R equals, I'm going to make the actual loop that I had. So R was 10 centimeters, let's say 0.1. Omega is going to be equal to 2. I'm just picking a value here. We can change it later. Mass doesn't matter, but I'll pick mass as 0.101, 10 grams. And then t equals 0, dt equals 0.01. Okay. I'm going to just make a rotating hoop. You got to start basic. I just realized that I don't know how to make a hoop. I made it before, but a hoop, I can make a disc. What did I do before to make a hoop? I want to make a hoop. Let's just check. Glow script, help. Object. So I got an arrow, a box, cone, curve, cylinder, ring. They do have a ring. Okay, great. Okay, so the position, the axis, the radius, the thickness. Okay, so it's a ring. Got it. Okay, so let's call this hoop. It's a ring. Its position is going to be the origin. Its axis, I'm going to have the axis coming out of the, I'm going to have the axis, yeah. No, I want it oriented. So let's have the axis in the x direction. Axis equals vector 1, 0, 0, because I want z up and down. I already did that before. I don't want to switch things up because it's going to make a mistake. Radius equals r. Thickness equals r over 20. I don't even know what that looks like. Let's just run it. And nothing happened. Okay, there. That looks pretty good. I want it a little bit thinner, so let's put 30. Let's try that. Okay, now I'm going to rotate it. I'm going to rotate it in the z-axis. So let's do a rotation. While t is less than 4, I'm going to run it for 4 seconds, rate of 100. So that I'm going to run it in real time. So what I want to do to rotate, I can just rotate the object with the rotate function. So hoop.rotate. So if I do that, I need to say about what point, and that's going to be the origin equals vector 0, 0, 0. What axis I'm going to rotate that about? I'm going to rotate about the z-axis. Axis equals vector 0, 0, 1. And then the angle. The angle I'm going to rotate, angle, is going to be equal to omega times dt. So each time I'm going to rotate it that much. Now I need to update time. T equals t plus dt. Let's just see if this does indeed rotate. Yeah, did it. And then we can look at it from the side. That's really one I wanted, but we'll just rotate it manually. Okay, now for the bead, I need theta. I'm going to need d theta, theta dot too. I don't want that. Let's say it's going to be 20 degrees. So let's make our bead. It's a sphere. Its position is going to be equal to, now here we can just calculate x, y, and z, and I'm actually going to do that. X equals r times sine of theta times x was sine omega t. Y is r times sine theta times cosine omega times t, and then z is negative r times cosine theta. And I can just copy that code and reuse it. And then down here, when I make my sphere, it's going to be vector x, y, z. Isn't that nice? Okay, the radius, it should be bigger than my bead. So let's do r over radius equals r over 20. Color equals color. Color dot yellow. Make trail equals true. Okay, let's just see if it won't move, but let's just see if it's in the right spot. Okay. Looks good. Okay, now I want to make it a little bit bigger, but that's fine. So now what we need to do is to update our differential equations and then use that to find the new value of x, y, and z for the bead. It won't be too hard. I can do it right here. Theta double dot equals. Now I go to my differential equation, which I have right behind me right there. Omega squared, times sine theta cosine theta minus g over r sine theta. Now I can use that to update my, oh, you can't even see that. I can use that to update my theta dot equals theta dot plus theta double dot times dt. And then I can update theta. Theta equals theta plus theta dot times dt. Okay, now that theta's changed, I can copy this stuff and post it right there. Now I can recalculate x, y, and z, and I can plot. I mean, I can update my bead. Bead.pos equals vector x, y, z. I don't know. What do you think? Think it's going to work? You never know, do you? You never know until you run it. See, that's not working. Okay, so what happened is I have it rotating the wrong way. So let's just put this as negative, I think. I think that's my problem. Yeah. Okay, let's make the bead bigger. Let's make this thinner and this bigger. Okay, that's pretty good. I'm pretty happy. Okay. Now, that's 26 minutes. That's more than the time I wanted to spend. But there are some really interesting questions that you can address. Of course, you can put this anywhere. I can start with this at, let's say, 60 degrees. Let's see what happens. It's kind of cool. And maybe you don't want to put the trail on there, but let's just do one more thing. Let's plot theta as a function of time just to see what it looks like, and then I'll give you some homework questions. G1 equals graph. Title equals, this is actually governor, right? That was the whole point of these rotating things. As you rotate it faster and faster, the bead will move up higher and higher in the thing, and you can use that to turn things on and off. So I'm going to put governor, even though it might be spelled wrong. X title is time in seconds. Y title is theta. Let's just leave it like that. And then width equals 400. Height equals 200. And then F1 is G curve. Color equals color.blue. And then down here I can plot F1.plot T theta. Okay, so it just oscillates back and forth. That's not quite simple harmonic motion, but that does lead me into my next question. Let's go back to the board, and I'm going to write down your homework questions for you, which I will probably answer at some point if I get bored, but I just don't want to make this video too long because I have class in a little bit. That's true. Okay, so number one, stable positions. Where can you put this ring? What value for theta will it just stay there? Okay, and then is it stable? This say equilibrium, and this is stable positions. Okay, I think that's, and then what happens as omega gets larger? That's good enough for now. Okay, so if you made it this far, congratulations, welcome, thank you for staying. Number two, I will put a link down below to the Python code for WebVPython. I will put the link down below for the playlist for all my classical mechanics videos if you want to go back and look at all the other Lagrangian problems and other things too that I've solved. Then that's that. I'll talk to you guys later.